Hey,
Well, everybody, welcome aboard this SBAU Astro Hour. I'm your host, Ron Heron. It's the weekly vlog podcast for the South Coast Longtime Telescope and Astrophysics Club we call the Santa Barbara Astronomical Unit, SBAU. We, the board members, movers and shakers of SBAU, and what I call a real brain trust for astronomy in Santa Barbara, California, like to get together on screen, online, through Zoom, Mondays, 11 to noon, like we used to do live at a little cafe for years on Santa Barbara Street. Kick around the cosmos, which deserves to be kicked around by a lot of people here. There's a lot going on. You can watch us live on YouTube or go to sbau.org. And happily, Vice President again, and let's meet the President on the left of my screen, Jerry Wilson. How are you?
Good morning. Good.
Married to lovely Pat Porgy. All the wives on the screen will also mention our supporters and members. There is our incredible outreach coordinator, Chuck McPartland, doing his latest cancellation. Which, you think it was raining, wouldn't you, a lot these days? And he's married to our merchandise manager, also named Pat McPartland. We are joined early on by Bruce Murdoch, who is a longtime active member, president of the Santa Barbara Theater Organ Society. But I think he likes astronomy even better, maybe. You never know. He's married to Bonnie. And here's Tom Whittemore, married to Maureen.
morning.
How are you, Tom? Former Westmont College science instructor, decided to retire from Westmont and bake bread for a living, and editor of our newsletter too. We're ready.
Ron, happy spring to everybody today.
Yeah,
I
think it's a couple of hours.
Right. This afternoon sometime, Chuck?
2:24.
Okay, thank you.
2:24, is that when the rain arrives? What are we talking?
No, that's spring.
That's spring.
Oh, okay. Well, that's what I wanted to say is that vernal equinox and the new moon are about the same, aren't they? Close together?
They're close.
Both
Pretty
today.
close.
All right. We're also going to talk about volcanoes on Venus, the remains of an ancient glacier, of all things, on Mars, and talk more about that incredible supermassive black holes versus dark energy. There's a connection. Some people think it's a new theory. And God knows there's so much to talk about. A marathon of Messier's up there, asteroid series, and let's talk silliness. These are the levity cartoons, silly science stuff that President Jerry emails all of us.
And speaking of silly, Tim might join us.
Oh, good.
Oh, yeah.
Oh, well, certainly. He commented on one of these. In the beginning, the universe was created. According to the scriptures, this made a lot of people angry and has been widely regarded as a bad move. Douglas Adams, all right. That's a good one. I don't know where you get these. Oh, this is the one that Tim didn't get. And it took me a moment too. Scientists have now discovered that frozen water on a neighboring planet, however, it contains toxins. So future astronauts have been advised to beware the ice of Mars.
Oh, that's pretty bad.
Shakespearean. That's as bad as a Tom Whittemore pun. Homegrown puns. Here's a couple of aliens in space cruising by our planet. Uh-oh, what's that one? Well, it's called Earth, and a mighty species called humans used to live there. Oh my, what happened? Hubris, stupidity, cow farts. All right, that would be methane or us. Rare footage of ducks on Jupiter. Looks pretty good. Oh, I see. I see the whole picture now. Yeah, I wasn't aware of the bands across, the strata. That's all one picture, superimposed, just like okay. Here is the Pi Piper. 3.14159, and goes on forever and ever, getting him out of town.
Wow.
Meanwhile, inside the box where Schrodinger put his cat, that dang thing is planning its revenge, just like it has on Chuck McPartland.
Same color too.
Yeah.
That's right. Schrodinger was allergic. Yeah, make this larger. We're inside an ancient, let's see, when Stan and Larry learned their office was right below the National Seismic Watch Center, they bang on the ceiling with a broom handle. Yeah, right there. Hit it again. The dang thing goes crazy.
That reminds me, well, our office, back when I started at Comtech, used to be upstairs from a Secret Service office.
Wow.
And so we used to Xerox bills, Xerox money, and cut it out and suspend it on a string and hang it outside their windows.
You suppose the LIGO centers, there's two of them have recorded earthquakes?
Oh, sure. They record
time.
trucks. They record the waves on the Oregon coast.
Yeah.
For those of you who don't know what we're talking about, it's supposed to record little tiny jiggles that represent two colliding black holes in a distant galaxy millions of years ago. Gravitational waves. Anyway, we got a lot to talk about, gentlemen, and I always learn, and I'm your question guy, and you guys have the answers. And where would you like to start, Mr. President?
There's two quick pictures that I thought were so cool that I put them up here, but they're not in the talking points.
The moon?
And this is one, it's in French, and this shows collapsed volcanic domes on the moon called Isis and Osiris.
Isis.
So they're lava, because we've talked about this recently before. Here's a very wide shot of them, Isis and Osiris. And
I got to tell you, the middle picture looks like coronavirus microscope pathogens. When do you get a long, straight, flat? Well, not flat, but look at that.
well, that's fully collapsed. And then
Like a
here's part
groove.
that haven't collapsed.
Okay. Is that viewable from, well, when everything is viewable now, but not much. We're about to switch over. New moon tonight.
It's good. Yeah, I think it's new moon
Yeah,
tonight.
we're pretty close, Ron. We're pretty close.
Yeah. And this one was too good to pass up.
Wow.
This is a picture of Jupiter from the South Pole,
Oh my God.
from Jupiter's South Pole, not from our South Pole.
But the Juno goes right under it in those huge elliptical orbits.
Yeah, red spots clearly visible, huh?
Yes.
Oh,
So
Yeah, but look at the
outer
activity
rim
right around
here,
the pole.
the outer
It's
rim
really
is the equator.
turbulent.
who knows how long that orbit takes? Which is it several months?
It's 10 hours for
10
Jupiter
hours
to
for the
rotate.
planet.
No, no,
And
I'm
20
not
means
talking-
Saturn.
I'm not talking about Jupiter. I'm talking about Juno's orbit around.
Oh, that's like 21 days, I think.
Okay. And the reason they do that is radiation, right? From
Yeah.
Yeah, so it only dips real close to the planet where the radiation is real quick, but in a short period of time.
And are they going to crash it like they did Cassini into Saturn, you suppose?
Into Jupiter. Yeah, probably.
When they get done.
Where are we now? Into the sky we go. This would be the Messier's.
Yes,
Bunch of
this is looking at obviously the Orion and Canis Major, two Pallas there, and this is a representative of. I didn't want to put up one picture to show the entire Messier marathon. You can't get them all in the single frame, but this is the prime time for a Messier marathon. And as you recall, the idea is between dusk and dawn, you spot all 109 Messier objects in one.
Actually, it's
single-
100. It's 110
Yeah.
in most counts.
I thought that was controversial.
I don't know. Most people go with 110 now, although M40 is just a double star.
That's right. And Chuck, which one is
Messier
M1? Which one is M111, Chuck?
Yeah, that's when it clouds over.
Yeah. So anyway, the best location is between 7 degrees and 33 degrees north latitude, but we're close enough at 34 degrees north latitude.
And there are no Messier objects down in the southern sky that you could see from Australia, because
Because he was in Paris.
that's right. Charles Messier was a northern hemisphere guy. Just
And
like
I was wrong on the Juno orbit. It's actually 54 days.
I see.
Oh,
okay, so it is almost 2 months.
Yeah.
Wow.
Yeah,
So
but
if-
the marathon run always starts with M74 and 77, which are tough to see galaxies. And it
Yeah.
always ends with M30 in Capricorn in the morning, which is pretty tough to see too.
Yeah.
Which is, I believe, a globular, right, Chuck?
Yes.
Yeah.
But Messier just named bright spots up there, right? He could have named
Yeah.
a star or a distant galaxy or a
Well,
globular.
he didn't know what they were, Ron. He was chasing comets and he was looking for things that moved, and these, these didn't move. And so he just started enumerating them. He also took a lot from Lacaille, and there was another Frenchman, Chuck, the other guy.
Yeah, and Machine.
That's it, Machine and Lacaille. Those are the two he grabbed some info from. Yeah.
Well, do you suppose he gave a number to a real comet and it disappeared, and now he had that
Oh,
number?
Yeah.
He
He
did.
discovered comets. Mhm.
Yeah, but
He discovered
these
16
numbers were for
comets.
non-comets, Ron.
Right.
Well, that's why I'm wondering if a comet took a number and then it disappeared, and whoops, let's put that on something that's not moving out of the range here.
Yeah.
No. He didn't put it in his catalog unless he knew it didn't move.
Right.
But if he were to visit an Australia, he'd have to add another 50 to 100.
At least.
Oh yeah, there's a lot of stuff. Chuck's been down there. So is Jerry.
And there's even bright stuff in the northern hemisphere that he passed over, like the double cluster.
Right. That's amazing. He did
Yes.
chop it down. Yeah.
So we got to make our own constellation animals out of these stick figures on the sky, don't we? The one on the left, that's an animal.
It's the unicorn, Monoceros.
Is that what that is?
That's a unicorn. Yeah, exactly, from the Greek, one horn.
And there's the big dog, and there's Orion.
Mm-hmm.
Oh, yeah.
And
Yeah.
the rabbit.
Is that gravitationally bound? I didn't think it was.
Is what?
What?
Double cluster, is that, I don't believe that's gravitationally bound, is it?
No.
No. They're hundreds of light years apart, right?
Yeah, that's what I thought.
Matter of fact, I'm not entirely sure that cluster members are gravitationally bound because they're drifting apart over
Yeah.
long periods of time as they rotate around the galactic center, because each star is in a different orbit. So they eventually disperse. So the Messier Marathon, if you want to know how to approach it, the strategy, there's a website by Don Machholz that suggests the search sequence so that you can get them all in. And
So Jerry,
using a computer go-to thing.
Jerry, if you don't mind me just jotting, Don was a member of our club, and unfortunately he passed away last August.
Right.
Matt Holtz. Yeah, and I actually have his Messier Marathon book that he signed back in the 90s. Really neat guy, really nice guy.
So you guys go through a marathon. It's kind of like a run every year, except you do it with your telescopes and you mark them off after seeing them.
You have a checklist to keep the
Yes.
early.
Yeah, and you try to do it all in one night.
Yes.
Do you ever not be able to find something?
Oh, sure.
Oh,
Cloud could come up.
The early evening and early morning things are both real hard.
Yeah,
They're very hard. Yeah.
and it takes a lot of Oreo cookies to stay awake all night.
And
Yeah.
your trackers or you got to move the telescope physically, or does it go exactly where it wants?
No, it's no fair using a computerized go-to telescope.
Yeah.
Oh, that's all right.
It's okay to do that, but I've always done them with my 8-inch homemade that has no motor on it.
We had a member who tried to do a photographic Messier Marathon. He was trying to image all 110 in one night. And for
Well,
that,
yeah.
you really want to go to,
You have to leave the lens open for a few seconds.
Many seconds.
depending on the object you're looking at. Yeah.
But with computers, like the president said, you just enter Saturn and it'll go to Saturn automatically.
Yeah.
No, regardless of where you are or what time of day it is. It's sort of like
Well, Saturn has to be up, or the telescope will complain to you.
all you need now is a Siri voice talking back.
Some of them have that.
Yeah.
They really. Here's the equinox explained. You want to, for the benefit of anybody that doesn't know, I would imagine this is basic. You got to know this. Some people don't. Solstice means what? The sun's right over one of the
The sun
Cancer.
stands still. The sun stands still. So it's both, it's from, Latin and then from Greek.
And it's when it reaches the northernmost or southernmost point and then reverses course.
Yeah. Hey, Ron, trivia question.
Okay.
How many degrees is there between the west-northwest and the west-southwest point? Chuck? Don't say anything.
Wait a minute.
How many degrees? 90?
No,
No.
What's the Earth's tilt?
Oh,
23.5 degrees.
yeah. In
Multiply
other
that
words,
by 2. Multiply
oh,
that by
it's 20, it's 23 or 27, I think, right?
23 and a half.
23 and a half.
So the answer is 47.
Oh, is that right? You double it.
Mhm.
And that's changing because of the Earth's wobble over time, isn't it?
That's like
it's not a
26,000.
wobble. It's just the tilt of the Earth as it goes around.
Yeah,
the
it's just the tilt, Ron. Yeah.
And this is where astronomy as a science started, because they were
Yes.
just timing things, and they were doing it so farmers could plant, they could keep the seasons straight. And
Mhm.
eventually, when people were going out and colonizing the world from Britain and Spain, they needed to have the time added in there so they could figure out where they were. So they invented longitude on the Earth.
Mhm.
And
in
this
order
is
to do
also where
that-
you get a lot of our holidays are around these events
Yeah.
because
Yeah.
in December people would celebrate, oh, the sun has started moving north again. We'll get more daylight and we've defeated the dragon that's going to eat the sun in winter and all that kind of stuff.
Yeah.
And then in June, it's like, hey, it's the height of summer, and
Right.
the equinoxes, it was like, hey, we're halfway. And then you have what are called cross quarter points, which are in between each of those. And that's where you get Halloween and Easter and all those
Yeah.
other things.
And
Yeah,
then, of
for
course,
long-
Easter
for
is,
longitude. Go
Oh,
ahead.
Easter is more equinox. Yeah.
that's
Yeah.
correct. That's correct.
Okay. So for longitude, people needed that on their ships, and they did that with clocks.
Yes.
And around the British Empire, every major port had an observatory in it. And at 1 p.m. in the day, they'd fire a cannon so that ships in the harbor could set their clocks.
You know
They'd
what?
drop a ball that was visible.
Yeah, they'd drop a ball too. That would do to it too.
And they do that at noon straight up.
No,
At
and
1 p.m.
yeah.
Well, the Scottish did that too. They fired the cannons from Edinburgh Castle, and they did it at 1 o'clock because, being frugal, they only had to fire one cannon rather than 12 if they were going to do it at noon.
Good one.
No, that's true. That's what the signs there say.
You suppose there's some evidence that suicides are up during the dark times of the Arctic Circle, or
Yeah.
I guess
Seasonal affective disorder, sad.
Yeah, they need light therapy. And yet
It helps. Yeah.
maybe we didn't evolve up there. We evolved in Africa and then went there, I guess. But as far as we know, nobody lives really much in the Antarctic Circle, do they?
Nope.
It's
I
all
wonder
on
if there's the corollary to that, because I've been in the Arctic during the springtime and the sun never sets. So
Yeah,
you
that's
never have
true.
any darkness.
What if there's a backside to that? Okay, what are we looking at, Mr. Jerry Wilson?
Well, let's do the one that doesn't have any pictures in it. Last week or the week before, we talked about observational evidence that the cosmological coupling of black holes was a source of dark energy. And I was reading a popularization. So this is the actual abstract from the Astrophysical Journal letters. And I just bulletized it to make the key point. The abstract is well written. But they looked at what they did. It's real simple. They looked at black holes in ellipsoidal galaxies. And they did this for most of cosmological history, which is just looking back in time and farther away. And they find that there's 10 orders of magnitude in mass across the things. And they needed a model for black holes. They dismissed the Kerr black hole one because that one is incompatible with an expanded universe. It blows up in infinity, and you can't have that. And you can't have singularities. So they had to have something else that described the core of a black hole. So they used a black hole model with realistic behavior at infinity that predicts that a gravitating mass can increase with the expansion of the universe independently of accretion mergers. That is, when we have these real large black holes right now, like at the core of our galaxy, that it didn't get there by just eating things, just soaking up dust and gas and stars. that they say there's a component of this expansion and growth of the black hole that is correlated with the black hole's interior solution, the mathematical solution of what's going on inside the black hole, and the expansion of the universe. To test this prediction, and it's the observational part, and this is the only black hole or dark energy thing that has any kind of observational support. They looked at, as I mentioned, the supermassive black hole in elliptical galaxies between Z of 0, which is right next to us, and 2.5, which is a certain distance back in time. If the Z equals 7, then that would be back about 13.5 billion years ago. So they found evidence, they say, for cosmological coupled mass growth among these black holes. That is, the black holes are just getting bigger because the universe is expanding. They're looking at two aspects of the same thing. The redshift dependence of math implies that at Z less than 7, that is in our universe, black holes contribute an effective constant cosmological energy density to the Friedmann equations. Now, the Friedmann equation is when Einstein came out with his general relativity, the mathematics is fairly hard to do. It's nonlinear, and Friedmann was one of the first, if not the first, to come up with a solution to it. To solve the gravitational field equations of Einstein, they make simplifying assumptions. And that's where the joke came from, that if a physicist were going to study a cow, he would say, okay, assume a spherical cow. You know, he just makes a simplifying assumption. And so they somehow the continuity equation requires that the black hole contribute a cosmologically as vacuum energy. What that means is that the universe, from quantum mechanics, we know that there is an infinite sea of virtual particles that's hidden from us. We know it's there because if you look at things in vacuum, particles in pairs pop into existence and then pop back out again as virtual particles. They do not obey physical laws when they're there, but if you supply energy to it, when it pops out, then they become real particles if the energy is the right amount, say their potential. And so we know that these things pop in and out all the time. They do it more when space-time is more highly curved than when it's flat. So it's credible to our intuition that these things would be more highly sucked into our universe inside a black hole where space-time is very highly curved. So, and that is the source of the vacuum energy. That's the infinite, or if you watched science fiction shows, that's the 0 point energy or the Z point energy, where they're always trying to, it would be a infinite source of energy if anyone could ever tap it, but you can't tap it unless you can curve space-time very highly.
So let me try to do a simplification of what you said. So these
That was a
cosmological particles,
simplification.
these virtual particles become real because they're in this curved space within the black hole.
Yes.
And so they end up contributing mass to the black hole, and that's why they see the mass growing quickly.
Right.
And then that also sort of imparts a push to the fabric of space-time that is then causing the expansion of space.
Yeah, that's very well
Which is that cosmological constant.
Right.
And that we call dark energy.
Yes.
But dark matter is not involved in this.
Right.
No, not necessarily. It depends what black matter is, dark matter is. But this is due to taking things out of nothing and making them real particles. It's sort of the logical extrapolation of Hawking radiation.
I was going to say that it's the inverse. Hawking radiation is the way that black holes lose energy.
They lose mass, but they do. Hawking radiation happens outside the event horizon. This happens inside the event horizon.
I thought Hawking radiation basically happened at the event horizon. So one of the two particles escapes.
Yeah.
Yes.
That's fine. But the one that escapes had to be completely outside the event horizon. Okay, so this defines terms. Kerr black holes basically means asymptotically flat space-time. Let's see, I guess I mentioned all these things. Vacuum energy, omega, lambda, because this is Einstein's cosmological constant, that's lambda. The omega is a term, oh, I didn't define that, but that's the coefficient of the term that Albert Einstein temporarily added to his field equations.
Yeah, that omega is usually the energy and matter balance of the universe.
Yes, exactly, well stated. Z is the redshift metric, of course, and it goes from
0.
Anyway, I mentioned that. A compact halo object, which I didn't cover in the other part, is a massive compact halo object. It's what it stands for. It's a kind of astronomical body that might explain the apparent presence of dark matter in galaxy halos. But that's yet to be determined.
What does MACHO stand for?
MACHO
what he just
stands
said.
for massive astrophysical
Oh, got it.
compact halo object.
Wow.
I should have blackened it massive astrophysical too. So it's different from WIMPs. That's the other end of the thing. So, and this is a refined calculation, which they they said that their results were consistent with Planck's data, and this is the result of the Planck data. It's the balance of what has been determined in our universe now from the recent Planck satellite. So 74% dark energy, 22% dark matter, 0.4% stars, etc., and 3.6% intergalactic gas. Brace yourself, Aaron, and dust.
Whoa. Well, that means a big part of the universe, if not most of it, was created after the Big Bang. It came out of nothing, right? Or was it all back there somehow in the point of the Big Bang?
The Big Bang was the release of all the matter and energy that we have in our universe at one time.
Including the uncreated that pops out of nothing and goes away, or
That's a good question. That's above my pay grade, so I'm going to pass on that. But if you study quantum mechanics, you can convince yourself that stuff, that infinite sea of 0 point energy is there. So this may be one way of tapping it, but not that we're going to do it. Now, this is another conundrum that's going on right now. These are galaxies pictures taken by the James Webb Space Telescope. And these galaxies are too big. They're really old. These are less than a billion years old, but they're bigger than our galaxy. And the idea has been that it takes time to grow a big galaxy because they accrete other things in other galaxies. So there's one of three possibilities from this that they're putting together. And this is another area of excitement for physics because it doesn't fit with the standard model here, the Big Bang theory. And so either there's a fast track for how galaxies can grow in the beginning, or the Big Bang theory is wrong. Time is just eluding, an illusion that far back, or the glow from these is coming from massive black holes eating things and not from just the galaxy. So that's a question, a tripart question that's got to be answered. Current research is going on about that, but science loves it. They seek these kind of things where you look at something and it doesn't fit anything that you know, and then you try and figure it out. So these are two areas that are working, really exciting times. So we also just escaped another Carrington event.
the old sun.
What's that?
The old sun is turning on us, except it.
Yeah,
facing
let me
the wrong
just see
way.
if I can capture this right.
Boy, that James Webb has been busy. These are huge early galaxies, or the other side of our sun, or wait a minute, the activity on the sun wasn't looked at by James Webb. There's no way that
not at all.
Yeah.
No.
Okay, let me get back to the meeting.
Probably Kit Peak or something like that.
Well, these are going to be SDO, the orbital things here.
Okay.
Wait, oh, I went
I
to
mean, we're orders of magnitude more vulnerable to a Carrington event now than we were then.
Yeah.
Yes.
I mean, they talked about being able to send telegraphs without batteries, and certain things were burning up, and that was just from the telegraph wires.
Huge auroras at the equator.
Yeah.
And this happened in the 1800s.
Yeah.
Can you see this?
Yes.
Okay. This is a satellite picture, and you see the big burp there going out from the sun. That's a coronal mass ejection that actually is going out of the other side of the sun. It's directed directly away from Earth. But the size of the mass ejection is apparently one of the biggest they've ever seen.
Wow.
And they're counting our lucky stars that we weren't on that side of the sun.
Wow.
That's Mercury down there.
Right.
Yeah.
Mercury.
I
didn't
assume.
get it.
Happened yesterday. This was a few days ago. This is 3/13, March 13.
The dark reddish disc is one of those filters in the middle. Uh-oh, lost it.
That
Yeah.
was a combination of images. They have an occulting disk that blocks out the sun, but then they superimposed another image in hydrogen alpha or X-ray on that to show you the actual size of the sun.
Okay, well, there's certain concepts I need explanation. A prominence, is this a prominence or a?
No.
It's not a prominence.
The prominence is something that happens down here on the sun, and the sun is just drawn in because this is the accretion or the
Occulting disk.
occulting disk that Chuck was talking about. And this is a filter that cuts down on the light because things are going to be really bright in here, and they don't want to scare the satellite.
They don't want to burn it.
That
Yeah.
too.
Down at Griffith Park, don't they throw the sun on the wall? I mean, through one of their telescopes?
Yeah,
Yes.
they have a solar telescope.
Would they have been able to see this?
No.
No.
They wouldn't have, huh?
The brightness of the sun just overwhelms this. That's why you need the occulting disk.
Right.
I see, okay. So the only name that you give this is an ejection of matter,
A CME, coronal mass ejection.
Rejection.
or, coronal.
So one of the satellites I worked on, a weather satellite for Japan, we had to we're up in space looking down on the Earth, but every now and then the Earth would occult the sun. And if the tracking was off on the satellite, it might accidentally pan over the face of the sun and stare directly at the sun. Our camera wasn't built to do that. And so we had to make it so that it could survive a 2-second direct stare at the sun. And we called it a 2-second ant burn.
You put a shutter in front of it or something?
No, we just made things real hard that way, and we depended on the thing to scan apart. We detected when it was staring at the sun, and then we hit the boosters and moved it aside.
Yeah, when I was at the Lockheed Research Labs, we worked in the X-ray region, soft X-ray. And we could look at the sun as long as we wanted to.
Yeah.
With a satellite. It was also with the Japanese. It's a solar X-ray telescope.
Yeah, we have a number of not X-ray, but we have a number of solar telescopes. that
Yeah,
look-
I mean, it's hard to call them X-rays, Jerry, because they're 171 angstroms. Because
Okay.
they're real soft. So,
Yeah.
Super ultraviolet.
Yeah.
Would it be fair to say, gentlemen, that the corona of the sun is like an atmosphere around the boiling
Yes,
plasma?
yes, it is the sun's atmosphere, Ron.
But it's
Okay,
not-
and it's hotter than just about everything else except maybe the center, isn't it?
It's
that's-
Well,
that's-
it's like 2 million degrees and the center's
right.
like 24 million
Right.
degrees.
but it's very tenuous,
Yeah.
That's right.
and it's shaped by the sun's momentary magnetic field.
Right.
And there's no, is it not plasma that's in the corona? There's no fusion going on,
It's
right?
No, it is-
plasma.
It is
There's
plasma.
plasma,
Well,
but no fusion.
no fusion.
It's not hot enough, Ron. It is pretty wispy. It's very wispy.
I've heard that it's 10 million degrees. I think I heard that figure.
Yeah,
About
but it's
2
not.
million.
It's not dense enough.
Yeah, 2 million Kelvin. That's what we're looking at, 2 million Kelvin.
Okay, and so this all happens with the corona? It doesn't start inside the sun? This explosion, this ejection you're talking about, what causes it? A sunspot?
Yeah,
Well-
magnetic activity on the sun, and you have reconnection of the magnetic field lines that have got a bunch of stored energy in them, like snapping a rubber band, and it splashes all this stuff out at high speed.
Mhm.
So it's electromagnetic in origin.
It's magnetic primarily, yeah.
Magnetic.
Magnetic is general.
Wow.
So did you ever have a plane, one of these planes that had a propeller on it made out of balsa wood?
Oh,
and
yeah.
Had a rubber
Yeah.
band down the middle of it?
Yeah.
And you'd wind the propeller up and the rubber band would twist up and twist up. But if you overwound it, then the big rubber band would start making knots on itself.
Yes.
Knots that come up. Okay, well, that's because the rubber band is a loop. And so magnetic fields are loops. They don't start and stop on anything. They do break and reconnect, but they twist themselves up in the sun. And these, all of a sudden, a knot will form, like a knot in your rubber band, and it will push out of the surface, and it'll pop out of the surface, and it picks up all this plasma with it, because the magnetic field, the plasma has to follow magnetic field lines. And so these things pop out of the surface, and they just throw this plasma out into the surface, and that's where you get these streamers coming out, and these big ones if it's a big enough knot that broke the surface of the sun.
But different latitudes on the sun, which we can't really see like on Jupiter, are going at different speeds, aren't they? And
That's right. Mhm.
That's part of what tangles up the field lines.
That's right. Right.
And so but there's no way you can see it in layers like you can on Jupiter. It's same thing.
You can map the magnetic field lines because they affect the spectrum of the light coming from that area. It's called the Zeeman effect or something like that.
Right.
Yeah, there's
So
the
you can
Zeeman
actually
effect.
map the intensity of the magnetic field lines.
Yeah, and you can look at it with polarizers, and you can actually see the magnetic line streaming.
Mhm. Mhm.
Well, I know it's apples and oranges, but there's something that goes on in Jupiter that is similar. The different levels, the different strata. Are
Oh,
going
they're both rotating fluid balls.
Yeah,
Right. Yeah, that's what you have to keep in mind, Ron. And so in the middle of the sun rotates about once every 27 days, roughly. As you go further and further up towards the poles, it's more like 36 days. So it's slower up there than in the middle. And that's why you get what Jerry was talking about, and Chuck, all the tangling of magnetic field.
Does science pretty much think all stars go through that, have the same thing? There's no way to prove it from a distance, I guess.
They have different amounts of it depending on their size and their age, but yeah.
Right. Right.
Easy. This is Venus.
Yeah.
Now Venus was not the one that had a glacier, is it?
No,
no,
Nope.
not unless it was way, way, way in the past.
Yes.
Yeah, right.
so this is a mountain on Venus taken in radar, and it was
Wow.
taken by the Magellan satellite back, I think, in the 70s or the 80s. And the information was stored on a new technology of the time called floppy disks. So it hasn't been terribly reviewed lately, but a group of researchers transferred the data to more modern access and looked at these old pictures from Magellan and decided that they convinced themselves that there is active volcanism on the planet. These are two different pictures of the same region taken in radar, but it orbited the planet for a while, and early on there's a caldera looking like this, and then it looked like this. So they're saying that it's probably an expanded vent. Here is a caldera maybe, and an unchanged vent, no big change. There is, now when you look in radar, you look at surface texture a lot. And so that's where the bright and the dark comes from, is from texture. And so there's a change in texture of this new flow ? From this region here. And one is fluffy, the new stuff is fluffy. Lava at the surface temperature of Venus, which is 800 degrees Fahrenheit and I forget how many, 90 Earth atmospheres.
Whatever it's 3,000 feet underwater would feel like.
Okay, good. So anyway, under those pressures, lava does not flow like it does on the Earth. It's much less viscous. It flows more easily. So, and that's consistent with this amount, with reflectivity of this material.
Well, now we're not looking at optical pictures. We're looking at radio waves. That's the only way you can see through.
Yes, we're looking at radar that was active. It's an active system. The Magellan probe sent down a radar beam, and this is the reflected signal from the radar beam. So it's not radar illuminated from sunlight. So this is the same region again at higher magnification. So you can see structure changes here, and you can see the change in the caldera here.
We're looking down into the mountains. Every one of those mountains is, okay, caldera means the top of a, they don't call those mountains mons, do they? Is that only on Mars?
Mons for this one.
Oh, is this a mons?
Yeah. That's the general term for planets for mountains.
Yeah.
Oh, okay. And that's the same one we just saw? This one right here, an artist rendering.
This is a computer-generated 3D model of Venus's surface of Maat Mons, M-A-A-T-M-O-N-S.
Maat Mons. And
one of the vents on Maat Mons appears to have enlarged and changed its shape in 1991. And that's what we were looking at, straight on this thing.
Okay, otherwise the heat on Venus is the thick atmosphere, the CO2 at 900 degrees is supposedly.
Yeah, we'll melt lead.
Yeah, oh, damn it, I wouldn't want to.
And Russian and US Venus probes and landers.
Yeah.
The Veneras. They said a bunch of Veneras, didn't they? Only one of them made it to the surface and gave us pictures.
Several.
I think they all made it to the surface, but one of them still worked when it got there. And it lasted for 20 minutes, I think.
46 minutes.
46 minutes, okay.
Wow. And then why is it so much thicker or heavier? Its pressure is 100 times.
It's really thick atmosphere.
Yeah, there's just more of it.
Okay. So Venus is 100 times thicker than us, and Mars is 100 times thinner than us.
So Venus is actually a climate change denier's nightmare.
Yeah.
It's a runaway greenhouse effect.
If it did have a normal atmosphere or climate at one time, none of those fossils would have survived, would they?
That's what they're trying to figure out, if it was ever like Earth or ever will be.
Wow.
It would be quite a challenge to terraform this, that is to make it like Earth.
But now the heat of that atmosphere on Venus is from the sun mostly, not from these rare vents. There's only a couple of vents, right? A couple of.
Right. It's mostly radiative forcing from the carbon dioxide. Same thing we're trying to do here.
Yeah,
trying to do it.
Jeez, Lord. Well, what's NASA going to do before you leave this topic? They're going to go out there again along with ESA, the European Space Agency.
Yeah, they're going to send probes to Venus again. And they're going, at some point, they're going to send blimp-like structures that float in the atmosphere and measure chemistry of the atmosphere without trying to get down into the acid layers and into the hot, high-pressure surface.
Wow.
Apparently, the atmosphere above the clouds is fairly friendly.
So somehow they're going to let go of blimp, and it's going to be full of what, air? Our air?
Something not as dense as CO2.
Wow. It'll die violently, of course, later, you know.
If it ever leaks, yes.
Wow. And what do you know a year on this? Any of you gentlemen know when we're going to launch toward Venus? How long it'll take to get there?
No, I don't.
That all depends on budgets, as usual.
Yeah.
Boy, there's a lot going on, a lot of probes.
Yes, there are.
Crashing into asteroids or circling Jupiter. Voyagers are still reporting in.
Okay, I do have a date here. The NASA is going to launch a probe called Veritas, and European Space Agency is going to launch Envision. They will arrive at Venus, and the data they return will, well, anyway, they're going to launch in Veritas is scheduled to launch in 2031.
Uh-huh.
A 3-year delay from what was originally planned. I guess it was 2028. And it will map the entire surface.
So we're just going to orbit. There's no way we're going to sit down in the middle of that.
They were working on some landers at NASA where, you know, the heat and the pressure are really tough on electronics. And so they were trying to make a lander that was mostly just mechanical, somehow, like a wind-up toy that they would send there that could survive the heat. I don't know how they were going to communicate with it, though.
Well, if the Parker probe is in several million miles closer and is orbiting the sun close up, they should be able to handle this problem, I would think.
Well, that has a heat shield pointed toward the sun to protect it.
That's true. A shield wouldn't do much.
We can build things that orbit Venus without burning up, as
Yeah.
long as they stay above the clouds.
How in the world did the Russians land all those Veneras?
Well, they had a parachute. They came down and they landed on the surface, but the heat and pressure were not expected, and they killed them.
Well, that one picture that we all see shows a kind of a jagged, rounded edge of the base of the damn spacecraft.
Yeah.
Looked heavy as hell. All right, a new comet is in the sky. Good old C2023A3.
This
Well, that's not what this is. And actually, the caption was wrong on this one. It said Z3, but this is a picture of E3.
Okay.
Not A3. I wrote
No,
down
run. This picture was of Z3.
Yeah.
And it's part of the article talking about the new comet A3 that hasn't come close enough yet to look like this.
Right. This was a reminiscence of what comets can be, recent comets can look like.
And here, it was when it was close to Mars in our point of view.
Right. And this one is A3 as it looks now.
which they just discovered, the Chinese.
Yes.
Was it the Chinese that found it?
Yeah,
Yeah, I guess
Sushinan
so.
or where, you know, I don't know how to pronounce it, but
Yeah, that's why I
that's
don't remember.
their observatory, I think.
It's Tsushin Shan Atlas.
Yeah.
The other one that we've been monitoring for months now is the 50,000-year orbit, ZTF. It's gone, or it's still out there?
No, it's still like magnitude 9. It's still in the region of Orion and Eridanus in that area, and it's heading out.
But this one's going to come in close to us next year, isn't it?
Yeah, hopefully.
Yeah, and this was discovered by China's Purple Mountain Observatory. That's in English. It's currently at 19th magnitude on January 9th.
Wow.
Only a telescope can see it, and how in the world would you program that? How do you
Big.
find it?
A big telescope.
A big one. Oh, okay. And it's coming in from above the platter of the solar system, the disk, isn't it? It's from the Oort cloud, I guess.
Yeah, or the
Coming from
Kuiper
some-
belt.
It's believed to have a closed orbit, so it originated somewhere, Kuiper or Oort. So here we are in March of 2023, right here, if you can see the cursor. And it shows it as being about 18th magnitude there. And then it's going to increase over 2024. And in, October. So early October, it's going to reach a very optimistic peak of -3.5, which is up there with Venus in the evening.
Wow.
But a more realistic value of probably magnitude 0.5, which is still very bright.
Kind of like the North Star.
Yeah, and then second magnitude, and then it'll go down and disappear pretty quickly over 2025.
Suppose we'll be able to see its tails.
Sure.
Yeah, I'm
Really?
pretty sure. Yeah.
There's going to be some cults formed We're gonna say the Lord is coming back next year. There it is.
The power of people to believe in crazy things just amazes me.
Mhm.
So Darwin is still active. So this shows the comet A3. You see it's very much out of the plane of our solar system. So it probably is from the Oort cloud, because the Kuiper belt roughly follows the plane of the of our.
Or it would have to have really interacted with something in the past to toss it
Yeah,
that way.
yes, right.
But is it 50,000 years like the last one?
I didn't see an orbit mentioned for this one.
Yeah, I didn't either.
Well, Haley's is under a century, isn't it?
73 miles, 73 years,
76, yeah.
76, yeah.
So I imagine that's a big thick cloud, that Oort, isn't it? The distant ones would take a long time. The inner ones would be your Haley's, I guess.
No. Halley's Comet doesn't reach out beyond Neptune.
Oh, it's not even in the.
Its farthest is out between Uranus and Neptune.
Oh. Well, it's almost like an asteroid, except you add the water and then you've got
Yeah,
tails,
yeah.
sunlight. We're back on the sky again, Mr. President. Serpens,
Yeah.
Ophiuchus.
So this is looking at, doesn't say whether this is west or east.
It says southwest.
Okay, October, November of 2024, after sunset. Oh, yeah, so it's the west.
Out to the
So
ocean.
this shows the path, which is going to be nice for us
Oh,
over the year from October 14 to November 17, 2024.
wow.
This shows a picture taken with a 0.4 meter, so that's about a 20-inch telescope. And the comet looks very much stellar. This is an easy comet to spot because of the arrow in the sky.
Yeah.
Yeah, there's also a brief discussion about how phase angle will make it brightly visible for the tail. Depending on the angle with the sun, forward scattering increases and the comet brightens as it gets down to being more in line with the sun. And so
Where are we with respect to that diagram right now?
Oh, way
This-
big angle.
Yeah,
Okay.
this comet, the reason this is here is that this comet is going to pass at a low angle with respect to the sun to us, and so it should show a very enhanced tail. So they're being very optimistic.
You're
And
supposed to be.
that's where they get this green line. Speculation.
Will it come within our orbit or stay outside our orbit?
Looks
Well, it's going to come, it looks like it's going to come within the orbit around in here, October 13, 2024. And I think that's going to be its brightest, and it'll pass low angle here. And that's when you can see the tail real well. Oh, it's coming this way and then up. So this is going to go down into, we're going to see it in the north, then it's going to be in our south, and then it's going to pop back up into the north and head out in that October to November timeframe of that chart. There.
Oh,
Excuse me. I guess I should have a button to press when I'm going to sneeze.
Mercury's orbit is a little off, a little tilted from the rest of the plane, you suppose? Mercury. Okay.
yeah, Mercury has a fair tilt.
So this is a picture of Mars, and it shows a glacier scar. I woke the cat up. So
It almost looks upside down, doesn't it?
Yeah.
I have no orientation for Mars. There's north right there.
Oh,
So this is what they're thinking might be the relic glacier. And
Relic.
on Mars itself, in the wide field, it's at the end of the Veil Marineris, at this labyrinthus, or the labyrinth, and this is the suspected relic glacier. So this is very close to the equator on Mars.
The explanations I've heard for the features they see in Valles Marineris there that look like erosional features from water.
Here,
and then
yeah.
you have this Noctis labyrinthus, which is this what they call chaotic terrain over here, was that this used to be an underground glacier type formation.
Yeah.
And some impact like this Udaman's crater here heated it up and it melted and the ground collapsed here and all the water ran out through Valles Marineris. And that's what gives you those erosional features.
But it's
Good
on,
explanation.
it's on the equator of Mars, not on the
Not-
poles.
It's near the equator.
Well, I imagine they must have had them on the poles as well.
Well, they still have ice caps. Yeah.
Yeah.
Oh, there's still glaciers on Mars?
There's ice caps. Yeah. That's
Yeah.
like a big glacier.
Oh, is it really?
Now, glaciers are where water ice flows like water, like liquid, but very slowly. And a lot of the ice on Mars is
Carbon
CO2.
dioxide.
And I don't know that off the top of my head, I don't know if that flows like ice or not, like water ice.
But there's no plans to land on the poles to get your water. That might
But we
be.
did land very close to the pole with one lander that didn't, well, not a rover.
And we don't see any glaciers these days through that orbit or that rover, right?
That it wasn't a rover, but it just scraped about 2 inches of soil off and it was on solid ice.
I'll be darned.
Was that carbon dioxide ice or water ice?
Yeah,
It
good
was
question.
water ice.
Wow.
Oh, okay. I didn't remember.
So someday in the far future, they'll be doing the same thing on our planet. There used to be glaciers here.
Used to be. Well, we do that now.
Yeah.
A lot
Well,
of
they're
glaciers are retreating. They're melting.
Yes.
Out in the desert, Death Valley, rocks can be seen, big boulders that have moved across the sand and left a trail.
Mhm.
Yeah,
Yeah,
that's
it's called
usually-
racetrack playa.
Yeah.
You know what that is?
It's kind of like
weird.
mud. It's mud
It's like-
kind of the base.
Yeah, they kind of roll on a Leidenfrost layer. It's easy for them to move. It's
Wow.
not a Leidenfrost layer. That's something different, but they move easily.
But this
I think it's
picture,
the wind. I think it was the wind that kind of pushed them on a
Yeah.
slicky surface.
really? Not
Oh, rocks in Death Valley.
Yeah.
They move very easily, Jerry.
Yeah.
And it's
Yeah,
the
I saw,
wind.
I
And it
saw,
was a mystery for a long, long time, which I think is now.
yeah, they caught it moving on film.
Well, now there's no rover near this,
No.
so we're only looking from down. Is there a plan, you suppose? It'd be nice to land there at Relic.
Yeah, they're
Rough
going to send a
terrain,
red
you
rover.
know.
They're going to send a red rover, Ron.
This is a good place for the helicopter, not so much for a rover.
Right.
Send Ingenuity over to check it out. I think we're down to the wire, but we covered a lot and I learned a lot. And I want to thank you guys, you gentlemen, for getting us on with number 107, I think, maybe 108. I'll clarify that next month. We're going to have tonight and tomorrow, or between tonight and tomorrow, vernal equinox. We get rid of winter 22, 23 and welcome the spring, even though some of us think it's been spring anyway. And then the new moon, right, will happen overnight. Amazing.
Yes, yeah, we're really close to one, Ron. That's right.
That's rare that we have them both happen, equinox or solstice at a change of the moon.
Yeah, I mean,
Yeah,
it's, I guess it's sort of a rarer match.
Yeah.
Yeah.
You know, it will put Easter on the 9th of April because it's the first Sunday after the first full moon after the equinox, and the equinox is today.
Right. Well, it's
So you wait for the full moon, and if it's new, you have to wait for a full one. and then you have to wait for the Sunday. Right?
That's right. Well, we talk about it right here on the SBAU Astro Hour. So we'll join you for number 108 or 9 next
Good.
Monday as we get ready for a talk on Zoom from the University of Toronto. Professor Dan Gilman will be our speaker on lensing and other things. So we'll see you guys later, and thank you very
All
much
right.
for educating us. Take care.